So we were talking about pressure and how that enables us to drink soda or rock stars. Pressure is predicted by kinetic molecular theory. So the pressure is the result of the constant collisions of the gas particles with the other particles and with the surfaces around them. This pressure allows us to inflate basketballs, tires on your bike. It allows us to breathe. We breathe by altering the pressure inside of our lungs, and that causes air to move in and out. Much of our weather is also caused by pressure. Pressure variations create wind, and meteorologists use variations in pressure to predict what the weather is going to be like. So we define the pressure exerted by a gas as the force per unit area. If you want to make an equation out of that, it would be pressure equals a force divided by the area. The pressure that a gas exerts is going to depend on a number of factors. One of those is the number of gas particles. So here we have, these kind of look like mason jars, two mason jars with gases. This one on the top has fewer particles than the one on the bottom. They are the same size. They have the same surface area. This one's going to experience higher pressure because it's going to have more collisions over the same amount of area. Here, the force is larger. The area is the same, but the force is larger. Here we have fewer particles, less force. So, which analogy? Oh, we'll go with the kindergartners. So if a kindergartner comes up and punches you in the stomach, is that going to hurt? Not much, no, especially if you see it coming. It's really not going to be much of a big deal. What if you have a whole herd of kindergartners punching you all over? Is that going to be bothersome? Yeah, that's going to get on your nerves after a while, right? Fewer kindergartners, less pressure. More kindergartners, more pressure. Each of these collisions is very tiny, but when you add them up, it becomes significant. There's the expression being pecked to death by a duck, right? One duck peck, no big deal. But if that happens over and over and over again, eventually, I don't know what would happen. Pecked to death by a duck. That's my life, but... Okay, pressure imbalance. If you drive up the hill to Grant Grove, it's an elevation of 6,000, 7,000 feet, you're going to notice some things going on with your ears. We say our ears pop. They pop as you're going up, and they pop as you're coming down. This can happen on an airplane as well. And it's due to the difference in pressure between your middle ear, your inner ear, and your outer ear. So in your ear, there's an eardrum, and this seals off the inside of your ear from the outside. It's impervious to liquid. When you feel like you have water in your ear, it's just stuck out here in this middle part of your ear. It doesn't go through the eardrum, unless your eardrum's perforated, and then you've got some other issues. So there is a space in here that also has air in it. As you go to a higher elevation, the atmospheric pressure outside is lower. So this pressure becomes lower. The pressure inside remains the same, and that causes your eardrum to bulge out. Now, that's not necessarily painful, but it's not really comfortable either. And as you go higher and higher and this pressure difference becomes larger, eventually the eustachian tube that connects your inner ear to the inside of your throat will release that air, and you'll have a popping sensation. It's released the pressure. On the way down, the pressure outside becomes greater than inside, and your ears need to pop again to let air in. Any questions? Pressure differences are why babies tend to scream on airplanes. They're not trying to get you. They're not trying to make you miserable. Their ears hurt. Well, pressure is something that can be measured, so of course we have to have a unit for it. The simplest unit to understand is the atmosphere. The atmosphere, it's abbreviated ATM, has nothing to do with money, is the average pressure on Earth at sea level. It's the pressure of 1 atmosphere of air. The SI unit is a Pascal, which is a Newton per meter squared. Newton is a unit of force. Square meter is area. So this unit of pressure is a force divided by an area. We're not going to use that one much, if at all. The Pascal is a much smaller unit than the atmosphere. An atmosphere is 101,325 pascals. You do not need to memorize this. If you need it in an equation, in a problem on a test, I'll give it to you. Another unit is a millimeter of mercury, which sounds like a weird pressure unit. Millimeter is a unit of length, right? And mercury is an element. So how can a length of an element be a unit of pressure? Well, this unit comes from the original barometer, which was something like this. A dish of mercury. Mercury is a really neat element. It's a liquid, but it's a metal. And so, it is quicksilver. It's a silvery liquid, and it's very dense. Unfortunately, it's also very toxic, and so we can't just play with it. Here we have a glass tube, and you make this barometer by taking this glass tube, filling it with mercury, and then inverting it into this dish. So this tube is open at the bottom, and some of the mercury will run out because it's very dense. No matter how long this tube is, the height of this column of mercury will always be about 760 millimeters in height. Because atmospheric pressure, just like with the soda, this atmospheric pressure can support a column of mercury that's only 760 millimeters tall. Now, atmospheric pressure varies with the weather, and so sometimes it's a little higher, sometimes it's a little lower, and that is reflected in the height of this column. We used to have mercury barometers in the classrooms, and I wish we still did because they were not hazardous, but people get all bent out of shape about it. But it's actually a long, very thin tube of mercury, and you look at it and you can see by the scale on different days the mercury is higher or lower. So this unit millimeter of mercury came from this barometer where you just take a ruler and you measure how tall is the column of mercury today. 760 millimeters is 29.92 inches, and that's just a conversion between millimeters and inches. So table 11.1, and also inside the back cover of your textbook, gives a summary of common units of pressure. The way this table is arranged, all of these things are equal to each other. So 101,325 pascals is equal to 1 atmosphere, which is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 14.7 psi, pounds per square inch, which is equal to 29.92 inches of mercury. They are all equal to each other. They are different descriptions of the same thing. One atmosphere is defined as 760 millimeters of mercury, so that is exact. Torr, millimeters of mercury, is kind of a weird unit, and so they had said, well, let's give it a more regular sounding name. They named it torr after Torricelli, who did the original experiments with the mercury barometer, and that sounds more like a unit, but we still hang on to millimeters of mercury, and so now instead of just one weird unit, we've got two. So a torr and a millimeter of mercury are two different names for exactly the same thing. Okay. You do not need to memorize all of these. I would recommend, just to save time, that you remember that 1 atmosphere is the same as 760 millimeters of mercury, which is exactly the same as 760 torr. But I will give you the pressure units on the exam. So We convert these units the same as we did any other units. Let's convert 1.25 atmospheres to torr. Well, our starting unit is 1.25 atmospheres, and we're going to convert this to torr. Pressure units can always be converted in one step. So we just need one fraction. I'm going to torr, so I'm going to write that on top. And I'm coming from atmosphere, so I'm going to put that on the bottom. So there we have the atmospheres canceling out. Get the units in place first, and then put the numbers. So the numbers, you go over to this table, and all of these things are equal. So you just pick the two that you need. Here I have 1 atmosphere. So over here, I'm going to put a 1 in front of atmosphere. And here I've got torr 760. 760 torr. So then you get out your calculator. 1.25 times 760. 950. Torr. We should always be thinking about significant figures. How many sig figs does this number have? 3. How about this relationship? It's exact. What that means is we don't have to think about it when we do a conversion. We're just going to look at this one. So then our answer should have 3. Does it have 3? It's ambiguous, right? There's a 0 without a decimal point at the end there, so we're not sure. So you could make it like that, 950, or what would be better is to put it in scientific notation. Any questions? Here we're given an equality and asked to fill in the blank. This is asking us to convert inches of mercury to millimeters. So 30.15 inches of mercury. I can do this in one step. I could do this in a lot more steps, but I like the short way. So I put millimeters of mercury on top, inches of mercury on the bottom, inches cancel out. I go looking for the relationship. I look in the pressure units. So here I have 29.92 inches of mercury. Okay, so I'll put that one down here, 29.92. And for millimeters, 760 millimeters, that's exact. Okay, so we've got 30.15 times 760 divided by 29.92. And my calculator's giving me lots of digits. How many sig figs does 30.15 have? 4. How about 29.92? It's not exact. Doesn't say exact here. That one's got 4. The 760 is exact. So I've got 4 and 4. My answer should have 4. So I'm going to write down the first 4. 1, 2, 3, 4, and 2 more, and then I'm going to round, so 765.8 millimeters of mercury. Any questions? So let's do another example. Convert a pressure of 173 inches of mercury into pounds per square inch. So pressure conversions, we can do these in one step. So 173 inches of mercury. I have one factor here. Inches of mercury is going to go on the bottom. Pounds per square inch. Pounds per square inch is PSI. Pounds per square inch. That's what the PSI stands for. Bless you. We go back to our table here, pounds per square inch. So 14.7 PSI and 29.92 inches of mercury. So I got PSI up here, Was it 14.9.7? 14.7, and down here 29.92. So we do the math, 173 times 14.7 divided by 29.92. Again, a whole bunch of digits. Well, how many sig figs in 173? 3. 14.7? 3. 29.92? 4. So 3 is the smallest, so I have to round this to 3 sig figs. So I'm going to write down the first 3 digits. Those are my sig figs I'm going to keep, and then I'm going to write down 2 more. And then this is PSI, and then I'm going to round. And when I look at this, the next digit is 9, so I round this 9 up to a 10. So this becomes 0 and this becomes 5, but I still need to keep that decimal place. So this is 85.0 PSI. Any questions?